Good morning, everybody. Welcome back to the class. We were talking about reaction mechanism in the last class, where we have seen about substrate, how the bond breaks in substrate, what are the attacking species, and all of those things. Then I told you about electron migration effects in the last class. We started with this particular topic. 4 electron migration effects are there. 3 of them are permanent. 1 is temporary. I've told you about the temporary one, which is electromeric plus E minus E. Both I have discussed with you. Plus I minus I also I discussed with you, that how many groups are plus I, how many groups are minus I, which all groups are those. Then we learned the order of plus I minus I, which was done by small mnemonic, which we have done here. So minus I, this was the order. Plus I, this was the order. Okay. We'll see 4 or 5 simple applications of inductive effect. Then we'll move on towards the next effect. Okay. So write down applications of inductive effect. Applications of inductive effect. All of you know that there are 3 permanent effects. So it is actually a wrong way to do the applications right now, because there is no just one effect working all the time. Okay, all 3 effects will be we have to check all 3 of them. So whatever examples I'll be telling you in inductive effect case is going to be those examples where hyperconjugation and resonance are not the deciding factor. Then finally inductive only becomes the deciding factor. Otherwise, whenever you get a question in the exam, don't check inductive effect first. I told you in the last class, the most strongest effect is resonance. First check resonance always. After that resonance or mesomeric, then check hyperconjugation. If still you are not able to decide the answer, then go for inductive. It is the weakest out of 3. Okay, weakest out of 3. So applications of inductive effect, these are not the application of only inductive effect, these are the application of all effects together. But here I'll just show you examples where inductive is the deciding factor. First major application is to decide the acidic character of any alcohol or carboxylic acid. Acidic character of alcohol or carboxylic acid or any other organic compound also could be given to you, like alkynes are also acidic, like some amines are also acidic. So how to check the acidic character? Beta, whenever you have any acid, I'm writing the acid as HX. When an acid behaves like an acid, it goes to water and it breaks down into H positive and X negative. So H positive I write it as H3O positive, X negative I'll write it like X minus. Now, all the organic acids which are there, they are weak acids, so they maintain this equilibrium. And you know that equilibrium constant of a dissociation of acid is Ka, dissociation constant of acid. In equilibrium chapter, you study that more the Ka, more the strength of acid. More the Ka, more the strength of acid. So strength of acid is directly proportional to Ka. Okay. Now, how do I make this Ka to be high? Whenever you want the equilibrium constant to be high, you need to form more and more product. More and more product. If the reaction goes forward easily, then Ka will be high. And when the product will be formed more, when the product will be stable. So stability of this X minus, we call it as conjugate base beta. Whenever there is an acid, whenever an acid breaks down and gives a H plus, it gives you a conjugate or a brother base. Okay, just call it a brother base. So it's a brother base of HX. Whenever brother base is stable, then strength of HX will be high. So strength is directly proportional to stability. Acidic strength is directly proportional to stability of conjugate base. This conjugate base in case of carboxylic acid will be RCOO minus. correct? When RCOOH will lose a H plus. In case of alcohols, it will be RO minus alkoxide. So this could be RCO minus, RO minus. In case of alkyne, it will be C triple bond C minus, like that. These are all kind of anions. All of them are anions. So when I want to stabilize the anions, what I should do? Anions are already negative charge. So if you want to stabilize the anions, you should pull electrons from them. They are already negative charge. Everybody is stable when they are neutral. So in order to stabilize this negative charge, you must pull the electrons. So we can say this strength or this stability of conjugate base is directly proportional to beta electron withdrawing groups, means minus I groups. So electron pullers make the acids better. Remember this as a note point you can mention. Pullers means EWG increases, pullers increase the acidic strength. Pullers increase the acidic strength, whereas withdrawers or the pullers are withdrawers, other ones are donors. Donors will decrease the acidic strength. Donors or givers, which is electron donating groups, decrease the acidic strength. Okay, so whenever you want someone to become a good acid, you start pulling electrons from it so that its conjugate base will become stable. But if you start donating electrons, acid will become poor. It will become a poor acid. For basic strength, just the reverse. For the basic strength will be checked for amines because nitrogen carry a lone pair. For the basic strength, just opposite. Donors will increase the lone pair density on the nitrogen, will make it a good base. Pullers will decrease the electron density and make it a poor base. So you can mention here as well, and vice versa. Donors means electron donating group increase the basic strength. Basic strength, they will ask you for amines only. Otherwise, they can ask you basic strength for these people also. Okay, their basic strength will be directly proportional to EDG. In this theory of, conjugate base acid theory, which you study under the Bronsted concept, Bronsted-Lowry conjugate acid base theory, you study that if an acid is strong, then its brother base is very poor. Acid is strong, brother base is very poor. That means if this acid is strong, it has withdrawing group, let's say, then this base will be a poor base because of that withdrawing group. So just simple to know, if acid is good, base is bad, and vice versa. So if I have pullers attached to acid, it will increase the acidic strength, and vice versa. If I have donors attached to bases, it will increase the basic strength. And also I can say now pullers, which is electron withdrawing groups, decrease the basic strength. Okay, I hope this is clear. So I'll just show you a few examples where this concept will be used. Hello, good morning, Ompal. For example number 1 I am taking here. Example number 1 I am taking here. Let's see some Ka values. Example 1 of some carboxylic acid. If you have formic acid, if you have acetic acid, if you have ethanoic acid, and if you have butanoic acid, propanoic acid and a butanoic acid. Okay. Now, in order to check inductive effect, I will suggest you one thing. Okay, Ompal. If you want to check for the inductive effect, I will suggest you one thing. Always underline the common part of each compound. So here 4 compounds are given. The common part is just COH, just COH. So the common part is COH. I have just underlined the COH. So this is the common part. Now, what are the groups attached to this common part? Here a hydrogen is attached. Hydrogen has no effect, beta. Hydrogen has no effect. In the last class we have seen hydrogen has no inductive effect, nor minus I nor plus I. This is a methyl. Methyl is a single carbon, it will have a plus I. This is more bulky alkyl, it will have more plus I. So it will have more plus I. And this is 3 carbons here, more plus I. So you will see that maximum plus I is present in the third carboxylic acid. Okay, present in the beta. I am from Haryana, Ompal. If you are in 10th class, that's good. You can just see whatever you understand here. Plus I minimum, plus I maximum, and here no plus I, no inductive effect. So what we understood by this is that maximum donation of electron is happening in the third one, and I just told you donors make the acidic strength bad. So this is a poor acid. This will be the best acid. So as the number of carbons increase in acid, you will see that its acidic strength will keep on decreasing. So formic acid is better acid than acetic acid, which is also fine. Better than propanoic acid, which is not so good. Better than butanoic acid, which is the worst. So this is the order of acidic strength. Or the order of Ka will also be this only. Okay, or the order of Ka will also be the same. So this is the one which we have to remember. Next example, let us see. Let us see one more example. Now I am taking a carboxylic acid, CH3, CH, COOH. Here a CH3 is attached. CH3, CH, COOH. Here a NO2 is attached. CH3, CH, COOH. Here a N, here a CHO is attached. These are the groups attached. And one more I'll take here. One more we'll take here, which is going to be CH3, CH, COOH, and here I am attaching a tertiary butyl group. And they ask you to find the Ka order for this one, order of Ka. If they are ABCD, let's say, then order of Ka they might ask for such a compounds. Now, I told you how to check. First thing is you mark down the common part of all the compounds. See here, the common part is these 3 carbons are common. Here also they are there, here also they are there, here also they are there, here also they are there. So this is what we can see as a common part of all the 3 molecules given to you. What is different now? The different is, what is different is these groups. Here it's a methyl, here it's a NO2, here it's a CHO, here it's a tertiary butyl group. Now when you are following the inductive effect, always we will follow a rule called as DNP rule, distance number power. Distance, first check distance, near the group, better the inductive effect. Near the group, better the inductive effect. Then number of groups. Means if distance is same, if distance is not able to decide the answer, then more the groups, more the inductive effect. Okay, let's say there is one group at second number carbon versus there are 2 groups at second number carbon. So 2 groups will have more strength of inductive effect than single group. And if the number of groups are also same, then only check that order of power that I gave you. Na Ritik, Shahrukh, na Farhan, na Ritik, Shahrukh, na Hinoti, Salman. That order that I gave you, you have to check that order only when distance and number of groups are same. For example, in this case, on second number carbon, I have a group, single group, second number carbon, second number carbon, second number carbon. So here distance became same. So I'm not able to check the distance. Distance is not able to decide. Next is number of group. here also one group, here also one group, here also one group, here also one group. So number is also not able to decide. Distance did not work, number did not work, so power will work. Check by power. Okay, let us see. CH3, all of you know, is a plus I group. It will send electron. It is a plus I group. NO2, naughty Salman, is a minus I group. CHO, Sonu Chaudhary, the Chaudhary was CHO, so this is again minus I. And any alkyl group like this is a very, very strong plus I. So this is plus I maximum, which is tertiary alkyl group. This is plus I minimum. So one is more plus I, one is less plus I. Obviously, the more plus I will make the acid very, very poor. So this acid is very, very poor acid. Okay, this acid is very, very poor acid. This acid is also bad because of plus I, so I am making it like this. This is also not so good. Minus I are the pullers, they will increase the acidic strength. So who is better minus I here? Power we have to check. NO2, naughty Salman, Sonu Chaudhary. So NO2 will be coming first. This is maximum minus I. This is minimum minus I. So the maximum minus I means it is pulling maximum electrons, making the carboxylic acid very, very happy. Making the carboxylic acid very, very happy. On the other hand, he is also happy, but not much. So like this. So the Ka order becomes Ka is highest for B, lowest for D. So it will be D the lowest Ka. Then comes A, which is also minus I. Then comes C, which is minus I, and D, which is maximum minus I. Okay, DACB. DACB. This is the order of Ka. Be very careful what they are asking. If they asked you pKa, pKa is actually inversely proportional to Ka. So pKa, which is nothing but negative log of Ka, whenever Ka will be more, pKa will be less. So pKa is inversely related to Ka. Okay, inversely related to Ka. So if they ask you the order of pKa in this case, you will give the opposite answer. You will say B has the least pKa. Least pKa means very strong acid. Then C, then A, and then D will have the highest pKa. Higher the pKa, lesser the acidic strength. Higher the pKa, lesser the acidic strength. So here D is the weakest acid. Okay, D is the weakest acid. This is how we can talk about the acidic strength of carboxylic acid. Now let us do one more example. Few more examples I'll just show you. Next one is, you can see here. Let's take, I'll just write the bond line structure now. These are the 4 compounds I've made. I'm putting a fluorine here. I'm putting a fluorine here. I'm putting a fluorine here. And here I'm not putting any fluorine. If anybody wants to answer, please reply to me. What will be the order of Ka? What will be the order of Ka? In this one also, we will be asking for the, let's say, pKa. I'm asking here. What is the order of pKa here? Let me write one more example for you, which is going to be, let's take CH3COH. Let's take CH2FCOH or CH2ClCOH. Let us take CH2ClCOOH. Here I am taking CHCl2COOH and CCl3COOH. Here also I am asking order of acidic strength. Okay. So if I do the first one, you can see here that the common part is these 4 carbons, 1, 2, 3, 4. Butanoic acid is the common part. Butanoic acid, butanoic acid, butanoic acid, butanoic acid. What is different in all these compounds is the position of fluorine. Here this is fluorine, which is -I group, attached on second carbon. This is fluorine attached -I on third carbon. This is fluorine attached -I on fourth carbon, and here there is no inductive effect. Okay. DNP, distance number power. First, distance is more important. Let's take distance first. Near the fluorine, better the inductive effect. So this fluorine is very near to COH. This will be -I maximum. So a 2-fluorobutanoic acid has maximum -I. Then comes -I medium. This will be -I minimum because it is attached on fourth number. So this is -I medium. This is -I minimum. That is -I maximum. -I maximum makes it the best acid. I told you before, pullers make the acid better. This is best, then this is not so good, but still better. This is not so good, and no inductive effect means it is poor acid. So A, B, C, D is the answer. A will have the maximum Ka, then B, then C, then D. This is the decreasing order that we are going to get. Okay. Next we have this carboxylic acid. The common part, all of you can see, is a cyclohexane carboxylic acid. So cyclohexane carboxylic acid, which is this part, this is the common part, beta. This is the common part. Underlining the common part, what are the differences in these molecules? Is the position of methyl. Here methyl is attached on 1, 2, 3, third carbon. Methyl is attached on third carbon. Methyl is +I. Here methyl is attached on fourth carbon. I am just counting the carbon from here, 1, 2, 3 respectively. Here respectively fourth position. Here respectively second position. And here respectively fifth position. So as CH3 is going away, this is the most farthest CH3. This is minimum +I. And this is going to be maximum +I. Donors make the acid poor. So this will be the worst acid out of these, which has the maximum +I. More donation happening, making the carboxylic acid poor. Least donation happening, making the carboxylic acid very, very happy. That CH3 is attached away from me. So I am happy. So D and P, distance only is working. So don't check number and power. Then this is nearby. So this will also be bad only. This is little far. So this will be okay. Okay. So pKa on the other hand, will be inverse of acidic strength. So best acid is D, least pKa will be D. Least pKa will be D. Okay. So the best acid has least pKa. Second best is B. third best is A, and the worst is C. C will have the highest pK. This is the order of pK. Okay. So how to check distance I told you. Now let's check number. So this is where number will come into picture. Distance, number, power. Common part is ethanoic acid is common. 1 carbon and COOH. This is the common part. This is the common part. CH, COH, CH, COH, C, COH. So common part is 2 carbon chain. Okay. Then here on the common part, no groups are attached, just hydrogens are there. We know hydrogen has no inductive effect. So here I can say no inductive effect. Here there is 1 chlorine. So 1 chlorine will have a minus I 1 time. Here minus I 2 chlorines, 2 times minus I. Here minus I 3 times minus I. Yes. So whenever the distance is same, everywhere chlorine is attached to second number, distance cannot get the answer. Number will get the answer. So 3 minus I, this becomes the maximum minus I, making it very happy acid. And this is the worst because there is no minus I. There is no minus I. So answer will be A, B, C, D. That's correct. Strength will be A, B, C, D, D being the best. So alpha trihalocarboxylic acid is much better than a normal carboxylic acid. So this is carboxylic acid, this is alpha halocarboxylic acid, this is alpha dihalocarboxylic acid, and the last one is alpha trihalocarboxylic acid. Okay, I'll give one more. You need to tell me the answer. Do this one and tell. Okay, these three I have given, and let's take one more, fourth one. Let's take one here. Now if we look at this one, how do we get the answer? There are 2 chlorines here. Okay. So as I told you, DNP, same thing will say DNP. Common group is the 3 carbon carboxylic acid. Propanoic acid is common. Propanoic acid is common. Propanoic acid is common. Propanoic acid is common. First thing, distance. Near the group, better the group. Near the group, better the group. Here the group is very near. Here the group is very near. So these two are maximum minus I's. These two are the higher minus I's. So first these two people say we are better than the others. We are better than the others because plus minus I is very near. Minus I very near. Among the two, number is same. So power will decide. Fluorine says I am maximum minus I. So fluorine person becomes maximum. This is the best acid. This is second best acid. So distance decides the first thing. Okay, then go to distance number 3, means third carbon pair. Now we are coming to third carbon. Here we have one group. Here we have two groups. Minus I 2 times. Here minus I 1 time. So distance is same. Carbon number 3. Then don't check power. Don't say fluorine is stronger than chlorine. No. 2 chlorines are stronger than fluorine because number is more important. So here number we are checking. This one says I am better. This is the worst. So between the third and fourth, fourth one is a better acid because there are 2 minus I groups present there. In the third one, only 1 minus I group is present. So here the order becomes for acidic strength. You will get it as the worst one is C, then D, then B, and A is the best acid. This is how you check the, yes, 2, 3, 4, 1. Not 2, 3, 4, 1. Two is the best according to you? No, beta. 2 is not. Yes, sorry, correct. We have written it opposite here. So we got the best one to be B. Yes. So B is the best, then A. So 2, 1. Yeah, not that. Okay, what you have written was not correct. This is the correct one. Second is the best. 2, 1, 4, 3 is the answer. Not 2, 3, 4, 1. 2, 1, 4, 3. Okay, Balaji, yes. So this is the way to check the acidic strength. Same thing you can check for alcohol also. Same thing you can check for alcohol also. Same thing you could check for, even alkane, alkene, alkyne. Let's say they give you alkane. They give you alkene. And they give you alkyne. Okay. Alkane, alkene, alkyne. Now I want to check which has more acidic strength. So best thing to do in any other case apart from carboxylic acid, you draw their conjugate bases. Beta, its conjugate base is going to look like this: CH3, CH2, negative. Its conjugate base would look like CH2, CH negative. So one of the H plus I am removing. I remove one H plus from here, one H plus from here, and I am removing one H plus from here. CH triple bond C negative. Okay. Now, I want to check which is more stable. Then always remember, a negative charge is always more stable on electronegative atom. And electronegativity of a sp carbon is much more than that of a sp2 carbon and then a sp3 carbon. That means most stable is going to be conjugate base of a alkyne. So if it is stable base, if it is a stable base, that means it will be a much stronger acid than alkane and alkene. So among alkane, alkene, alkyne, please remember, alkyne is a stronger acid as compared to alkene and alkane. Alkene and alkane are not at all acidic in nature. Alkynes are highly acidic in nature, almost like an alcohol. So this is the one. You can take an example of alcohol as well. Let me take one alcohol. So I take phenol versus ethanol versus isopropyl alcohol versus tertiary butyl alcohol. So here, beta, what is the common part? There is no common part, only OH is common. What is the OH attached to? Here the OH is attached to a benzene ring, which is a minus I group. Okay. Alcohol's mother alkyne nahi, benzene hai. So benzene was a minus I. This is a plus I. This is even a stronger plus I, secondary plus I. This is a very, very strong plus I, which is tertiary plus I. This is maximum plus I. And this is minimum plus I. This is medium plus I. So what did we see? Because they are acids, donors make the acid poor. So this will be the worst acid. Tertiary butyl alcohol will be the worst acid. Phenol will be much better than all of them. That's why phenols are stronger acids than normal alcohols. Okay, one reason is inductive effect. Another reason will come, which will be its stability of conjugate base due to resonance also. So the phenoxide ion will be very stable because of resonance. Minus M of the benzene ring will be seeing there, not just minus I. But this question can be solved by only minus I, so I can tell you the answer here. So the order becomes for the acidic strength, or let's say order for pKa. So the best acid is first one, pKa will be least for the first one, and pKa will be very high for the last one. pKa order I am writing, pKa, not the Ka, okay, which is inverse of Ka. So this is the way to check the acidic strength of some carboxylic acids and some alcohols I have told you. So any question coming from here, I hope you will be able to answer them now. Moving towards the next one, next application, application number 2 is to check the basic strength of amines. To check the basic strength of amines. Okay. Already I have given you the note point that donors will make the base better. Donors increase the basic strength, pullers increase the acidic strength. So whenever you take an amine looks like this, RNH2. It is a primary amine. If it goes to water, it will collect a H plus from there, giving you RNH3 positive and OH negative. So Kb is the dissociation constant of a base, just like Ka for the acid was there. If you want the base to be more basic, you want its brother acid, this is the brother acid, conjugate acid. You want the conjugate acid to be happy. You want the conjugate acid to be stable. Conjugate acid is a cation beta. It is a cation. It is a cation. How do you make a cation stable? How did you make a carbocation stable? By sending electrons to it. By sending more and more electrons to it so that its positive charge can neutralize. So electron donating groups will make him happy. Electron donating groups will make him happy. So we can mention that basic strength or basic character also you can say is directly proportional to Kb. Basic strength depends on stability of conjugate acid, directly proportional to stability of conjugate acid, which depends directly on electron donating groups, EDG, plus I groups, and inversely to electron withdrawing groups, minus I groups. So when you put more and more plus I, it will make the bases strong. When you have more and more plus I, it will make the bases strong. So let us see a few examples of this as well. The most common example which comes is between a primary, secondary and tertiary amine. So when I take a primary amine, first example, CH3NH2. If I take a secondary amine, CH3NHCH3. If I take a tertiary amine, CH3NCH3CH3. Okay, beta. So as you can see here, in a primary amine, NH2 is attached to only one plus I group. Distance is same. On the very first atom, there is one group. On the very first atom, there are two plus I groups, which will increase its lone pair density. So here lone pair rich nitrogen will be there. Lone pair will be more visible, or more density of lone pair will be there. Here 3 plus I will send so many electrons to nitrogen that nitrogen will become a very, very good base. A lot of electron density here. So any which way you can check, either you can say that plus I increases the density, or you can say plus I stabilizes its conjugate acid. So here a tertiary amine is the best amine. So if I write the basic strength, this is the order of basic strength. This is the order of basic strength. Okay. In the same way, let's do one more where we have bases like this. And I ask you for the basic strength of these. All these questions can be solved now if you know the basics of inductive effect. I want you to tell me the answer of this. Okay, so again DNP here I'll be checking 2341. All right, let us see. DNP, distance is same everywhere, beta. Distance is same. So number is also same. Only directly power I will check. NO2 is a very strong minus I person. NO2 is a very strong minus I. So minus I. CH3 is a plus I. Fluorine is also a minus I. Sonu is also a minus I. So out of these, NO2, naughty Salman, minus I maximum. Sonu Chaudhary car mein, this is minus I medium. Father collector, brother inspector, this was minus I minimum. This was plus I. So the only good base is this one here. 1 is the best. Beta 1 will be, 2 is the best. Yes, 2 is the best. So 2, then minus I minimum. Yes, 3 is also good. Then medium minus I, yes, this is bad. And then the first one, maximum minus I, will make it very, very bad base. So yes, you have written correctly. Very good. 2, 3, 4, 1. 2, 3, 4, 1. That is correct. 2, 3, 4, 1 is the order. Good. Okay. So this is how you check the basic strength as well. Can you tell me for these two? If I take this one versus this one, versus this one. So these three if I take, if I ask you for PKB, beta PKB will be inversely proportional to the KB. PKB will be inversely proportional to the KB. Can you check for this? So for this one, what I will see is this, although it can be solved by resonance effect also, but by inductive also I can solve it. NH2 is attached to a phenyl ring here. Phenyl ring is a minus I effect, we know. Here it is attached to alkyl. Alkyl is plus I. Here it is attached to two alkyls. So 2 times plus I. Plus I 2 times. So this will be maximum plus I, making it very good base. Minus I will make it a bad base. So this base is bad, means its PKB will be highest. So PKB order will be highest for A, then for B, lowest for C. So C is the best base here, CBA. This is the increasing order of PKB. Okay, same way one example of carbocation, one example of carbanion also I have given you. Okay, this is how you can check for inductive effect. This is how you can check for inductive effect. Now we'll study the next part of it, or let's see some example of carbocation and carbanion as well. Then we'll move to the next one. So we'll see here third application, which is stability of reaction intermediates. Stability of reaction intermediates. But there are 3 intermediates that they will ask you. First one is carbocation. So when I take carbocation, stability of carbocation Carbocation is electron deficient species. It has a positive charge. So when you want to stabilize the carbocation, you need to send electrons. So put electron donating groups here, plus I. And if you put withdrawing groups, it will make your carbocation sad. So for carbocation, donors make it happy. For carbanions, it will be opposite. So first let us look at carbocation examples. So first example of carbocation, let me take a simple one. CH3 positive, CH3, CH2 positive, CH3, CH positive CH3, and tertiary butyl carbocation CH3C, CH3, CH3 positive, like this. So this is the basic example which every book will tell, the very first. In NCERT also you will get like this. You can also call them as primary, secondary, tertiary carbocation. Primary, secondary, tertiary carbocation. This is the primary, secondary, tertiary. First one is also primary. But whenever you check the stability of carbocation, no, as a habit, don't check inductive effect first. Okay, be careful. Be careful. Number 1, first check resonance. That if any carbocation is undergoing resonance plus nothing pi, this thing is there, or plus nothing lone pair, then that will be a much better carbocation. So any carbocation which can, go for a walk here and there, if it can go here or there, by resonance, if a carbocation can get delocalized, that will be the best carbocation. First check this. Second, then check number of alpha hydrogens, which we call it as hyperconjugations. Okay. So first thing what you will do, you will check for the resonance. If resonance is there, that is the best. After you have checked for resonance, then you check for the second thing, which is going to be hyperconjugation. What is hyperconjugation? We will do later, but number of hyperconjugations will be equal to the number of alpha hydrogens. What is alpha carbon? Alpha carbon is the carbon next to the CH2 positive. So here there is no alpha carbon. Here this is the alpha carbon, this is the alpha carbon, this is the alpha carbon. These are the alpha carbons. So after checking for the alpha hydrogens, if still you are not able to decide, then check inductive effect. So then come to inductive. So 99% of the questions, you don't have to check inductive effect in carbocation stability. For the acidic strength and basic strength, mostly inductive only will work. But for the carbocation and carbanion stability, first always check resonance. For carbocation, check hyperconjugation. For carbanion, you have to skip this part. For carbanion, there will be no hyperconjugation. Okay. And then check inductive. At last, check inductive. At last, check inductive effect. This is the thing which you have to take care about in checking the stability. So, in these ones, let us see. First one, no resonance, no resonance, no resonance, no resonance. There is no resonance. This plus cannot undergo any resonance. Then check alpha hydrogens. Here, 0 alpha hydrogens. 0 alpha hydrogens. Here you see these three carbons, these carbon carry 3 alpha hydrogens, so 3 alpha hydrogens. This carry 3, this carries 3, so 6 alpha hydrogens. And here 3, 3, 3, 9 alpha hydrogens. So actually it's not a question of inductive effect to decide. It is decided by hyperconjugation only, that more the alpha hydrogen, more is the stability. Lesser the alpha hydrogen, lesser is the stability. So that is the reason why a tertiary carbocation is always going to be better than a primary carbocation most of the times, but always check the alpha hydrogens first. Okay, I hope it is clear. So this is the example number 1. Now I am giving example number 2. I will give you 5 minutes to solve. You can tell me which carbocation do you think is the best. Just give me the order of stability of carbocation here. Here we have a positive charge on this carbon. Here we have a positive charge on this carbon. Here we have a positive charge on this carbon. Here we have a positive charge on this carbon. Okay, take your time. Then you can decide and tell me. 2 is the highest. That's good. So number of alpha hydrogen directly I'll check. There is no resonance in any one of them. So for the first one, the number of alpha hydrogens, this is alpha carbon which carry 2 hydrogen. This is alpha carbon which carry 1 hydrogen. 3 alpha hydrogens are there. For this one, this is alpha carbon which is carrying 3 hydrogens. This is also alpha carbon which is carrying 2 hydrogens. This is also alpha carbon which is carrying 2 hydrogens. So here the alpha hydrogen in the first one were 3 alpha hydrogens. In the next one we have 3 plus 2 plus 2, 7 alpha hydrogens. In the next one we have only 1 alpha hydrogen. And in the next one we have 4 alpha hydrogens. 2 on this side and 2 on this side. So yes, B becomes the best. 2, 4, 1, 3. That's good. Very good. 2, 4, 1, 3 is the answer. Two, 4, 1, 3 is the answer. Okay. Let's see one more. Okay, if I look at this one, everybody, then here also, see, inductive effect will most probably will not be seen in the carbocation stability orders. It's mostly going to be the other factors which will work. So in the first one, we have a resonance present plus nothing pi. So one resonance is present. Plus nothing pi, there is a resonance possible. In the second one, there is no resonance possible. In the third one, there is no resonance. In the last one, two resonances are possible. This plus can go resonance here, plus nothing pi this side. Or this plus can go resonance here, plus nothing pi this side. Okay. So yes, there are two resonances possible here. So this is the best carbocation which has more resonance structures. No beta. Fourth will be the highest beta. Okay. Then this one which has one resonating structure. So whenever there is resonance means the positive charge is alternate position to a pi bond or alternate position to a lone pair. That is always the best. So this is two resonance. This is one resonance. Among these two, this is tertiary, more alpha hydrogens. So alpha hydrogens. Now you have to check alpha hydrogens. After checking resonance, then go for alpha hydrogens. So here we have 7 alpha hydrogens. Here you have 4 alpha hydrogens. So that's why this 7-1 is better than the 4-1. Okay. So answer will be for the stability. Worst is second. Second. Then we have third. Then we have first, and fourth is the best one. This is the order of carbocation in this particular question. Okay, just one. Okay, good. The next thing is, let's check for the stability of carbon ion. Stability of carb anion. Beta, in carbon ion, there is no case of, hyperconjugation. Okay, never check alpha hydrogen. Just check any carbon ion is going for resonance. That means the negative charge is alternate position to a pi bond. That will be the best first. So more resonance, more stability of carbon ion. Then directly check inductive. So stability of carbon ion carries a negative charge. It is directly proportional to electron withdrawing group, means minus I. Inversely proportional to electron donating group, which is plus I. So in carbon ion case, yes, you have to look for inductive effect. Here the major effect will be inductive only after checking resonance. So first thing, check for resonance. If there is no resonance, then directly check inductive effect. In any normal carbon ion. Okay. So if I look at a carbon ion which looks like this, CH3 negative, CH3, CH2 negative, CH3, CH negative, CH3, and CH3 whole thrice C negative, like this. Okay. No resonance, no resonance, no resonance, no resonance. Directly go for inductive. Here, three people are sending plus I, which will make it very, very unstable. 3 people are sending electron, it will become too much negative, very, very unstable. So the best one is primary carbon ion, which has no inductive effect happening from 3 hydrogens, like that. So we don't have to check any alpha hydrogen or anything. Second example, let's take one more. You will understand from this point of view. If I give you this carbon ion versus I give you this carbon ion versus I give you this carbon ion versus I give you this carbon ion. So if I give you these 4 carbon ions, we have to check where is the resonance first. First one though has no resonance, minus nothing, nothing. Next one also has no resonance, beta. There is no resonance, minus nothing, nothing. For resonance to be present, you should be able to say like this, minus nothing pi, minus nothing pi. Here, minus nothing, nothing, minus nothing, nothing. Here, minus nothing pi. So yes, one resonance is there. This minus can go for a walk like this. This minus can go for a walk like this, becoming stable. One resonance is there. Here, this minus can keep going for a walk. Minus nothing pi, nothing pi. A lot of resonance is there. Minus nothing pi, nothing pi. So, fourth one is the best one here. 2 resonance. This will be the best. 1 resonance is also very good. Among first and second, resonance is not working. So, check inductive effect. Check what? Inductive effect. Beta, in inductive effect, DNP, everything looks same, just that there is a ethene here. There is a ethene group here, means alkene group here. And here there is a alkane group. We know that alkenes have little bit of minus I. Alkenes have little bit of minus I. Because of sp2 carbon, it will be pulling electron, making it somewhat better than the last one. This is the worst. This is somewhat better. So answer is A, B, C, D. Answer is A, B, C, D. Let me show you one more example, beta. If I take a carbon ion, which looks like this, CH2 minus NO2, CH2 minus CH3, CH2 minus CH2NO2. Okay. If I see here, beta, in the first one, there is a resonance, minus nothing pi. So yes, pi bond is going for a resonance. And also NO2 has a good minus I also, making it very good. So resonance is there. Here, no resonance. Here also, beta, no resonance, because this NO2 cannot show resonance here because there is no conjugation. Minus nothing, nothing. No resonance. So first one is the best. First one is the best. It is undergoing resonance. Second versus third, check inductive. In inductive, you check the common part. The common part is 2 carbons. Common part is 2 carbons. Here NO2 will apply a minus I effect. This NO2 is having a minus I effect, making it also good. This is the worst. So answer will be B the worst, then C, A the best, B, C, A. Okay, like this. Quickly note it down. We'll keep the class till here today. I have told you how to check the stability of carbocation, carbanion, acidic strength of carboxylic acids, alcohols, as well as I've told you some examples of basic strength also you can check. So 4-5 applications we have seen in the today's class. I hope it is clear to everybody. Okay. Bye bye.